when by chance I came across a paper which is older than I am, then I started thinking, like, why is there no system out there which is based on pentagons?
Today, I'm joined by Felix Palmer, the creator of A5, a new global grid system that's rethinking how we divide and analyze the planet. Felix's background is as fascinating as the system itself. He started in physics at Oxford, moved into visual programming, and ended up building the web-based visualization framework many of us use today, DeckGL.
For the last 3 or 4 years, my main project of focus has been an open source project called DeckGL, which lets you visualize big data directly in the browser.
What began as a quest for better visualizations eventually turned into a question that reshapes how we think about grid cells and even the geometry of the Earth.
It's not so hard to split a 2D surface into equal cells, like you can just have like a chessboard or something like that. But to wrap it around the world, then you end up with different trade-offs.
That trade-off led Felix down a rabbit hole, one that would challenge the assumptions built into systems like H3 and S2.
And it's actually even more of a error with H3, because so in this case, it wouldn't make any sense if you were comparing, say, how far people are going to travel to work and saying, okay, in London it's 10 miles, in Madrid it's 10 kilometers, therefore it's the same thing.
In this episode, we dig deep into what makes A5 different, how it achieves true equal area cells across the globe, and why pentagons, not hexagons, might be the future foundation of spatial indexing.
I mean, you can see a grown man making models out of paper of like pentagons, or painting a door in your apartment with pentagons show just quite how into this thing you'd get.
From DeckGL to A5, from visualization to geometry, this conversation is a perfect blend of art, math, and geospatial design thinking. As you know, the future is spatial, so let's get into it.
So first of all, super excited to be here. Thanks for the invite. My background to getting to this point is maybe a bit convoluted or unusual. I come from a background of physics, which I did a master's at Oxford in. But what I always liked were more kind of visual things and more like the engineering side of things. So I didn't carry on in physics. I got into programming, and especially programming which has got some kind of visual aspect to it. This led me to geospatial over the years. And for the last 3 or 4 years, my kind of main project of focus has been an open source project called DeckGL, which is a web-based visualization framework, which lets you visualize big data directly in the browser. So you can do all sorts of visualizations on top of a map. So this is showing migration between different places in the US. You can also do these kind of geospatial bar charts, or anything really. And through kind of working on this, then I basically got interested in, well, I basically kind of started by accident working on this grid system, where I spent a lot of time looking at these visualizations basically. And there's existing visualization systems out there, which basically try and separate the world into these grids so we can visualize data on top of it. This one I'm showing here is one called S2, which was made at Google, and it separates the world into squares. And another one that's very popular is called H3, which doesn't use squares but uses hexagons. And essentially, I've spent time working on the kind of code that draws these things on the screen. So when by chance I came across a paper which is older than I am, from the 80s, which is called Equilateral Convex Pentagons which tower the plane, then I started thinking, like, why is there no system out there which is based on pentagons, essentially? If you look through this paper, then it goes through all the different pentagons you can use. And at the bottom, without actually understanding all of the maths, I came across these diagrams and I thought, well, these actually look pretty close to what we have in these kind of global grid systems. Maybe I could try and build a grid based on these ideas myself.
So I think, what's particularly interesting is that there's, at least with some of the grid systems and some of your work in DeckGL, is that there's obviously challenges in rendering spatial data, kind of in the browser, right? That's a very, I think, unique, specific challenge. And some of the grid systems certainly help with that. I'd be curious to hear a little bit about that. And then from there, the grid systems also embed a lot of spatial information in them. And I think there's a lot of positives with that. I think there's, certainly things that it can help with. But then, as with any abstraction of data, there's also downsides. And I think, understanding not just the visual aspect of it, because that's, I think, the most first striking thing you see is like understanding the data this way. It helps make data really approachable, and it can improve the performance of, data in the browser. That's one step. But then also the other underlying pieces that, you might not see when you first look at these systems, that it encodes and embeds spatial information. And what you've done with A5, I think, does it in a really unique way. At least the first time we talked, I was pretty, I saw some of it when I looked at the website, because I, kind of keep an eye on all the things you're working on. But at the same time, it was like, the more we got into it, it made a really compelling case for that. So can you talk about like where it starts from like the rendering and visualization challenges, and then go through to, okay, why A5? And then what are some of the challenges that, when you encode spatial information in a grading system, what are the, pros and cons of that?
Yeah. It's actually a very good point, because as someone who's working on a visualization framework, then I started from the visual side of this project, which maybe is a completely different end to someone who's a data scientist, where they'd start by designing some kind of algorithm or like data format. And just if I could just show a couple of the sort of early images I started with. So the first step I did is starting kind of from this paper, like, can I translate what I have here onto like a flat surface? And then I tried to see, well, look, can I put this onto a globe? Because this is actually kind of like the key challenge in these grid systems, which is it's not so hard to split a 2D surface into equal cells. Like you can just have like a chessboard or something like that. But to wrap it around the world, then you end up with different trade-offs. There's no simple, nice way that you can convert a flat sheet of paper to sphere. So the first thing I started playing around with is, do these pentagons that I've even seen here kind of nicely mesh into a whole world? Because it's not obvious that they're going to do that. And I noticed that it was possible to move these like shapes that were in the paper into larger sort of pentagonal faces, which kind of interweave, and then together they can actually be moved into like a bigger sphere. So it was kind of at this point that I started thinking like, okay, it's possible to visualize this, but as you say, like, is it actually possible to do something useful with this? So the first stage was just kind of getting something on a map. And this is the very kind of visual part of these grid systems. Actually building some kind of like, or answering some question with these systems is not necessarily then trivial. So it's kind of like, why have such a system? So if I just go through one of the examples that I have on the website, let me just rotate it. So what these are very, very good for is showing like the spatial distribution of some kind of data. So this is kind of like a 3D bar chart of accidents in the United Kingdom. And for this to actually be meaningful, then each of these cells has to have the same size. If one of the cells there is going to have a different size to another one, then it's going to end up being kind of misleading, because it's not going to aggregate things equally. And this was the kind of key differentiator that I was trying to kind of achieve with A5, is to basically build a system which had truly equal area cells, because pretty much all of the sort of, at least when I got started, the ones I knew about systems out there, then they have cell sizes which vary in size. And this means that certain kind of analyses that you can do with them are not quite, they're roughly correct, but they're not exactly correct. That's what I was trying to get to with A5, essentially.
Yeah, I think when you look at or first approach some of the cell systems, I think that's like the first most striking thing that people start to understand. I mean, and I think it'll be worthwhile to dive into, I think you had some really interesting comparisons with like H3 and stuff like that. But H3, visually it looks, the same. I think like some people then can associate, when you see something that visually looks the same, you think it's all the same, and underline that it's not the case, right? So I think you had listed like the two core challenges, or there's a couple different challenges here, but or stages as you've talked about. I mean, the first one being just having complete coverage, which was that's one difficult challenge, and then the second, having equal area. obviously A5 has complete coverage. I was curious to talk about the coverage and then the granularity and the scale it can go down to, which was probably the thing that caught me most off guard in a good way, was how granular A5 can go. And then I want to talk about the concept of the equal area and kind of what some of the real world impacts of that are. And I think, for anyone who hasn't worked with, a grid system before, it kind of helps to think of it like a map projection. With any projection, you're projecting the round surface of the earth onto something flat, and you have to make a trade-off there. There's no way to do that to have those trade-offs. So I think just acknowledging that grid systems work the same way and understanding the trade-offs that come with that will be really important. So I want to add that context, especially for folks coming from a GIS world where that's kind of the thinking they have. So can we talk about those two pieces of the puzzle there from the start, or I know there's 4 pieces, but let's start with those two to talk about first the kind of coverage problem, and then the equal area problem, and some of the trade-offs there.
Like a sort of geometric level, what you're trying to do is cover sphere, which is a curved surface, somehow in equal-ish shaped and equal, like similar shaped cells. So I actually have a couple of models that I made out of paper to help myself understand this. I have them on the screen here as well, but sometimes it's fun to make stuff out of paper. So here I have 3 pentagons, which, as you can see, then they can't be put together into a flat surface. It's kind of the same as this dodecahedron, which is the shape that A5 is based on. It's basically 3 of these pentagons that you have here. Now, what you can keep doing is you can cut these faces up like this, and that's basically what I've done on this guy. So we basically go from something like this to something like this. And a grid system, all of them are pretty much doing some kind of variation on what I just described there, is that you start with some sort of flat surfaces. So in A5, it's pentagons. In S2, you're starting with a cube. And in H3, you start with an icosahedron, which is made of triangles, 20 triangles. And then you have to find a way of sort of applying a tiling grid pattern onto each of these faces in the way that there are no gaps. So here, if I go to the next resolution level, then I start replacing it with these particular pentagons that I have here. And this is the pattern that I found in that paper. And the nice thing about the pattern is that you can keep reducing the size of these pentagons and keep making them smaller and smaller and smaller. And you get closer and closer to a sphere. Like if I kept doing this, if I kept increasing this resolution, apart from crashing on my computer, then I would get to something that's like a perfect sphere. So on a geometric level, this is how you would construct one of these systems. Then comes the kind of computer science challenge of like, how do you make such a system useful? How do you kind of index it? How do you refer to each cell? And I think that's something that we can come back to a little bit later. But I would just like to show this other demo, which is showing the contrast between H3, which is using hexagons, and the big difference is and this is because of the choices that were made in the design of these systems. I'm not saying one of them is better than the other in all cases. It just means that in certain use cases, it's better to use one, and in other ones, it's good to use another. And by way of background, then H3 was a system designed by Uber to basically help them analyze the data, which is data for ride sharing in cities. And that's a very specific use case. And for that use case, it undoubtedly worked very well. This is a very successful company. But this system has now been taken and used in many, many different contexts where maybe it doesn't make so much sense. And like one particular weakness of the system is the fact that globally, the variation in the size is quite big. So the difference between the largest cell and the smallest cell is roughly 2x. So this one is twice the size of this one. Now, if you're zoomed into this region here, and with H3, these cells would get smaller and smaller and smaller, it doesn't really matter because they're roughly the same size. But if you'd like to compare the cells in like one city on one continent and the cells in another one, they're not going to match. It's going to be almost like if in London you're using miles to measure things, and in Madrid you're going to be using kilometers. which of course like seems like ridiculous. But it's in a way similar to what you'd be doing with H3, and it's actually even more of a error with H3 because the difference is double, whereas a mile is only 60% more than a kilometer. So in this case, it wouldn't make any sense if you were comparing, say, how far people are going to travel to work and saying, okay, in London it's 10 miles, in Madrid it's 10 kilometers, therefore it's the same thing. But if you have a grid system which doesn't have equal area cells, then this is actually what you end up doing.
It reminds me of whenever I talk to someone who doesn't come from like the geospatial world, when you talk about the choices Google Maps made for map tiling, where when they originally created those, the Mercator projection works great when you want to create a bunch of, individual kind of equal size squares to tile map data over the web. What it doesn't do is it preserve the shape of, many different things and distorts it. So certain things look bigger than others. And when I apply that same thinking, if I was to go back to an H3 map and know that certain things in these other areas are much larger, so your aggregations are innately off based off of that, and that variance carries across the entirety of the globe, it can really change your perspective on what you're looking at by a lot. And I think that that was when I took a step back and really thought about that. It can really distort kind of what you're seeing from a data perspective and understanding those different things. So I think having that kind of grounding is really interesting, and knowing that you're able to achieve these equal areas across the globe with A5 is really interesting. What is there anything that makes the shape, the Pentagon, like uniquely suited to this? Like what is why? I guess maybe the question why Pentagons and what makes them like what makes them special? I guess.
So if I could just first, I forgot to show this example here, which is kind of carrying on what you were saying with the comparison of two places, because I think it shows this two-city use case quite clearly. So this is basically showing like a density of Airbnb listings. So I can just switch to this point view, and you can see that the kind of 10-kilometer circle, the scale on these is the same. And we might want to make some kind of like computation of like where we have the highest density between these two cities. Say I want to decide I'm a tourist agency, I want to invest in one place or the other. We want to see where tourists are going more often. If you choose something like H3, and to be fair, I have chosen two cities where this is like particularly visible, but they are realistic cities, then on the left-hand side, then it looks like we have a much, much, much higher density thing. We have 999 per cell, and here in Oslo, we only have like 400. So you might conclude, wow, I have way more density of accommodation in this area. But that's not actually true. If we switch it to A5, which has got equal area cells, then it's actually much closer. It's like 600 versus basically 500. And this mismatch is not just because like some random chance of where the edges of these cells are. It's because the cells in H3 are roughly double the area here than they are in Oslo. So you're kind of not comparing like with like, to answer your questions like why Pentagons, then like kind of one answer is because that's what I found fascinating, and that's the kind of like rabbit hole that I totally went down. I mean, you can see a grown man making models out of paper of like pentagons, or I think I even showed this earlier, painting a door in your apartment with pentagons, show just quite how into this thing you'd get. What is nice about them is that they basically let you tile the whole world in, let's see this example again. They let you tile the whole world in a single shape. So you basically have like no outliers. You can also do this with like other shapes. You can do it with squares, but they also get deformed, or triangles. But you cannot do it with hexagons. If you look at H3, then it's a hexagonal tiling system, but you'll notice that there's a couple of pentagons. So each of these kind of light colored ones here, there's 12 of these across the whole globe. And it doesn't matter how much you zoom in, they are always going to stay there. So this is like a particular quirk of H3, which just comes from geometry, and there's nothing that you can really do about that. Now, if we're comparing H3 and A5, then H3, it chose to try and preserve the shape of these hexagons as being as round as possible. So that is something that's really, really nice about H3, that you have this nice symmetry where each cell has got 6 neighbors, and I'm ignoring the pentagons for now, and they are all kind of nicely related edge to edge. Now, this is something which A5 doesn't do. Like some of the cells, then they have neighbors which are not edge to edge, like this one and this one here. They kind of meet vertex to vertex. So depending on what you're trying to visualize or what you're trying to solve, then one system might be better than the other. Maybe you don't care that the cell sizes are only roughly equal. Maybe you want to analyze like flow of people or traffic, and then having a more simple relationship between those cells and the neighbors is kind of what you'd like. But what A5 has solved is a way of splitting it into equal size cells with like no exceptions. And it even handles the fact that the world is not an exact sphere, but it's an ellipsoid for you. So all of these cells are truly the same size, and that's not something that you then have to allow for in your analysis.
And does that allow it to go to that really like small area level? Like that's also the thing I found really interesting was how granular you can get with A5. I think you said it was like 30 millimeters squared is the lowest one. Is that am I right with that?
Yeah, you're right with that. Like with each of these systems, then like in theory, if you have like a nice kind of like pattern, you can keep going lower and lower and lower and making smaller and smaller cells, and you can go down to theoretically the atomic scale. The question is like, what do you need to label each one of those spheres? And typically these grid systems, and this is actually the problem they're trying to solve. They're trying to reduce something that's like geometrically complex to something that is a tractable problem for databases. So you basically want to label each one of these cells with some kind of like ID, some kind of identifier. So if you look down here at the bottom, then this is a 64-bit integer. I've expressed it both in binary and in hexadecimal. And basically all the grid systems are doing something similar to this. Like as I move around the world, then this number is changing, and this is like a unique value. And this is actually why we go through all of this fun to build these systems, is so we can reduce this complicated problem of like, how do I represent areas and places on like a not quite spherical celestial body in a database? And the answer is, well, you separate them all into these cells, and each of these cells has got like a certain identifier. And then if you want to look up if two shapes overlap, or if you want to just store something by a certain ID, then you can use the 64-bit ID. So to get to actually answering your question of like how far down can A5 go, then because of the choices made in designing this index, the way that we actually assign a value to a cell, then it can go down to a very, very small size. I mean, it actually goes down so far that the base map Libre, stops zooming. Like I can't actually zoom in far enough because it cannot go to the millimeter scale. And the reason H3 doesn't do this, so H3 goes down to roughly 1 meter, is because of the choices they made in this index. Like they have just not optimized for this particular use case. And it kind of makes sense because the problem that they were trying to solve was like, can I get a ride in a taxi? And you normally book a taxi from a street or something. You don't actually care if it comes to the exact like millimeter where you're standing. So it's a difference in choice in the design. But one thing that is very neat about being able to go so granular with your ID is that you now have an indexing system which can be used for representing areas. So you might have like a list of cells, and that's going to represent, say, I don't know, some city in France or something like that. If you can have like 20 of them. But if you go close enough, then these are basically representing points because they're just so granular that the size of it is, as you said, like 30 millimeters square. So something like this size.
I think what's so cool about that is I mean, there's a number of different things, but the fact that all of that's encoded. I mean, like you said, it almost is like a data like a database problem where you're trying to encode a lot of information in that, in that binary or in that string, whatever that might be. And the scale at which you can achieve, but also the relationships that's embedded in that. There's a lot of information encoded in that, right? When you take that little bit of data and you can understand what's within that, that's pretty impressive. And that's, I believe you kind of list that as your stage 3 challenge, right? How do you create this index that
Yeah.
can
Which
encode all
definitely
of
was a
this data
challenge.
and information in it? What now? So we have, we've kind of gone from first coverage, then area. Now you're basically not just encoding how this should go, but all these spatial data in that. What were the specific indexing challenges that were presented with this, and then how did A5 kind of uniquely solve them, which I think is actually even more interesting than, each layer gets more and more interesting as we go down the rabbit hole here. So
Yeah. I mean, this has been a serious rabbit hole, I can tell you. And my fiance can certainly tell you. So first off, like these ideas, and I didn't come up with them myself. They kind of come from S2 and then H3. In fact, even the naming scheme A5 is kind of following this like pattern that was set by these systems. And essentially what's interesting about this indexing problem is that it comes to finding some kind of path that links all of these cells together. So if we kind of go back to the beginning, where we're first taking this shape, this would be quite easy. We can just label these 1, 2, 3, 4, 5 all the way up to 12, and we have our indexing scheme. Then as we go down the resolutions, we basically need to find a way of indexing within each one of these triangles that we have on this shape here. And the way we do this is with what's called a space filling curve. So this triangle here is mapping to one of these guys here. And then what I can do is I can take the triangles and link them together, and then I have a curve which is going to cover the whole world. Basically, we need to find like a pattern that's going to start in one corner and sort of zigzag its way around, ideally without overlapping over itself too much. I couldn't find a way that didn't overlap at all. But what is nice about the algorithm that lays this out is that you can sort of change the resolution, and it's going to have sort of like self-similarity to itself. And you can also sort of like see that as I go and reduce like the path that I have here from one part to another, then it's kind of like painting the triangle shape. It's like filling it in. It's not just like randomly zigzagging. Like if I do sort of half of it, then what I have left is also kind of one sort of unified shape. So basically the problem of indexing the cells becomes a problem of how can I join them all up with a line? And then if I say I'm one segment along the line, and this will have index 1, this will have index 2, 3, 4. That's not quite how it works, but in principle, that's basically what you're doing here. And one visualization I like in particular is if I sort of remove these cells and start increasing the resolution, then you'll see why it's called a space filling curve. Like this is a line, but it ends up basically going through every single point that on this screen, at least, it looks like it's completely covered. So what this lets you do is turn basically a way of having like a 2D point. So here having X and Y into a 1D point, which is like how far along am I this line? And then you can get this space filling curve, which is in a triangle, and join them all up across all these pentagons. And you end up with a line that starts, I think it starts somewhere in Alaska, and it kind of loops all the way around the world and then comes back to the beginning again. So we've basically found a way of zigzagging a single line around the whole world so that it covers every single point. And this is what actually gives us, in the end, our index, because this line is inherently like one-dimensional. You could think of it as just a piece of string and measure from one end to the other. And it's laid out in such a particular way that it passes through the world in like a nice order, which lets us index the cells. There's actually one more hidden little thing here, if I may continue.
Yeah.
The way that I've chosen this line to go, it's not random. And this comes back to your question of, has A5 done something different to be able to go down to this very, very, very small level? The answer is yes, because if we sort of take the first roughly 80% of this curve like this. So it first starts on the North Pole, it goes through America, across Asia, eventually it gets its way all the way to Australia. Then what it does is it actually covers the land mass of the Earth first, and then it goes through the oceans. It's actually much easier to see if I switch to this kind of like unfolded visualization of it, where you can see that the first 8 sort of pentagon faces, that's where everyone lives. And this is mostly ocean or ice, and also Hawaii. But, sorry, Hawaii, it's not my fault that you're in the middle of the Pacific. But what this lets us do is not actually waste the indexing space on oceans, which as humans, we probably don't need to measure down to millimeter scale. Whereas measuring millimeter scale on land is pretty useful. Like if you want to do some kind of like engineering works, then that kind of level of resolution might be something that you might need. Now, to be clear, like A5 does work globally. It's just that it has an ever so slightly lower resolution in this segment of the world. But that's a lot of like memory space that it's saving from doing that. And as far as I know, this is the first spatial index that has chosen to do something like this. And it's what lets it go even higher resolution, definitely than H3, but even more than S2.
And so, I mean, what's really interesting is how you can take the globe and the Earth and all the pieces that are unique about it, and you're reducing it, not reducing it, but in a way, you can build it into this geometric kind of math problem in a way to efficiently sort and order data of the Earth, right? That's kind of a lot of the work that we do, and sometimes you forget all the pieces and the groundwork that went into that, whether we're working in geospatial and all the things that have been done to enable that. And then when you take a look at it in a completely new way and try to sort that out, there's a lot of efficiencies that can be brought from that. I think one that you had talked about is kind of when you have to do this problem of joining data sets together, right? And hierarchy and things like that matter. What does all that set up to in terms of like the practical problem of like, hey, I have a bunch of data, maybe it's population data or temperature data or things like that. What does H3 or what does I gotta edit that out. What does A5 bring as a unique kind of proposition there that maybe like an H3 or an S2 don't, that allow us to do that kind of joining problem, more uniquely? Because that's one thing that I've seen has been always tricky, is kind of like when you have these data sets that might have a high level of detail or granularity or something like that, and you want to preserve that accuracy, but then going to a grid system, you're giving up some of that. From that perspective, how does that matter in terms of all those different levels from hierarchy and all these different pieces once you add it up to kind of this, seemingly simple problem of a spatial join?
Yeah, so like this joining problem is definitely kind of like, it doesn't seem, you don't notice it until you hit it, where basically everything is happening somewhere, and by running some kind of like data science problem, we're trying to get some kind of insights. So if you're trying to combine information from like different data sources, say from different government agencies or from any other source, then if you're dealing in one case with like polygons, which are like city outlines, the other one might be some kind of like grid, then you're going to hit this issue of like, how can I like join these two completely like different shaped things? What you don't want to be doing is in your database query, be like calculating the overlap between one shape and another shape. That's going to be like very, very slow. And the way that this problem has been basically solved with these grid systems is that you convert whatever data you have into one of these grid systems. And then you don't actually have to think about geometry in this kind of more like complicated way. If you have like a multi-polygon that has holes in it, then it's actually like a difficult shape to reason about. Like, how does that intersect or overlap with something? Maybe you think that the bounding boxes overlap, but one thing is in the whole of the other polygon. Like, it just gets very messy. But if everything can be reduced to like a list of IDs, then your problem becomes how many of these IDs overlap, or how can I join on essentially that ID. In terms of like how A5 is better here, then the sort of two key differences are like, how far is your granularity going to go down? And the other one is the sort of equal area. If you're just talking about joining, I think you could argue that it doesn't really matter. You can still join the data sets. It's just that the data set that you're going to have as a result is not going to have equal area cells. So maybe the insights that you get from it are not going to be like as good. It's going to be much harder to answer certain types of problems because when you're going to try and extract something from that answer, you're going to have to always account for the area. In terms of the accuracy, then it really depends on your data. Like if you're dealing with like large scale data, on the size of like miles or kilometers, then it doesn't really matter that the system can go down even in a more granular way. But if you're trying to work with something like satellite imagery, then there the features are getting very, very, very small. And in particular, H3 there is just not going to be good enough to represent this kind of like small level detail. The smallest feature it's going to be able to represent is something that's a meter across.
I think one of the key things that helped some of these systems really start to grow to get to your final, the final boss of grid systems. How do you get that into people's hands, and how do you help them use it? I think H3 did a good job of building this ecosystem and allowing people to use that in different languages in different places, be that in a database setting to port into a lot of databases and SQL-based systems. It's in Python. It's in, you've done a Java level and all these different places. How have you started to build that out? Because I think very quickly you've done it so that it can be brought into a lot of different languages. Where did you start, and kind of how did you port that into things like either Python or Rust and stuff like that? And then what's kind of the vision for that in the future, and where's that going to go?
Yeah. So that's like a super good point. Like it's one thing to just go and define a bunch of maths and algorithms. But one of the most valuable things about a system like H3 is that it's been widely adopted. So if you have your data in one system and you want to share it with someone else, they're going to sort of know what to do with it. And it's likely that the tool chain that they're using is going to be able to read it and work with it, visualize it, analyze it. Essentially, it's this kind of problem of how do you establish something as a standard. So after sharing A5 a few months ago, where the focus was very much on visualization and JavaScript as the language, then I really focused on trying to port it to different languages, because it's not really that useful if you can visualize something with A5 if you have no way that you can generate it in your kind of data science workflow, which is often going to be in something like in Python. So now, a few months on, then there are equal like fully featured ports of A5 in JavaScript, in Python, and in Rust. And actually with this, I kind of also tried to try something new, which is very much kind of in vogue right now with like generative AI. And if you look at some of the other grid systems, so again, I'm going to compare to H3, then the way they've implemented their whole ecosystem is that they wrote the core library in C++, and they have bindings for other languages. Now, this obviously works for them. It makes it possible to use H3 in many, many languages, but it makes it more difficult to collaborate and contribute to the system. If you're, say, a JavaScript developer, then how do you, start writing C++? It's just a big jump. So what I tried to do instead is use large language models. Particular Claude Code was very impressive here, in basically translating the code base with the help of very kind of granular tests into these different languages. And it was actually very interesting that translating it to Python made me realize there was a bunch of like very hard to see, but very important precision issues, which I hadn't spotted before. So by porting it, I actually made the whole code base much, much, much better. And as you can imagine, if you're trying to write maths where it needs to be accurate down to the millimeter across the whole globe, then it's sort of 10, 11, 12 decimal places. It's very, very easy to miss something like this. But if you have two implementations and they're giving you different results, then you instantly see, okay, there's something going wrong here. Once I had the Python version done, then what really blew my mind was the Rust version. Now, I've never written a line of Rust in my life, but I was able to basically get this agent to take the TypeScript version and the Python version and use those along with like very, by this point, like good tests to produce a Rust version, which works. I almost started this as like a sort of hopeless experiment. Like, this is not going to work. I'm going to have to find a Rust developer, but it really did work. So, going forward, then I like to think of this as a code base that's not written in just like one language, but one that's written in at least 3 languages. And I'd be able, or anyone would be able to come and contribute into one of these languages. And then we could port it across to the other 2 automatically. Because this is something that the LLMs are incredibly good at, this kind of pattern recognition, changing something into a different context. As long as it can be like tested. And this is a very mathematical type of code, so it definitely is very nice and testable. One other thing I'd like to mention is also the community involvement that I've had here. So in particular, one project that's called vgrid. This is a Python package which actually lets people work on like multiple different grid systems and compare them. Then this has been super, super useful in building like utilities on top of A5. So here you can use it with GeoPandas. You can do even more things than the library can do itself. So you can like compact and uncompact. You can convert from a polygon into A5 cells. You can do binning. And there's also a bunch of like comparisons between all the different DGGSs here as well. So it's actually a very nice tool for people kind of looking to compare the different systems. I'd recommend them this, and also by the same author. So this is by Fang Quach, is an integration into QGIS. This is actually something which has only just come out yesterday. So if I can just share a couple of images of this, you can now, and it's not just for A5, it's for all of these grid systems, or within QGIS, do all of these kind of conversions that we've been talking about. Like, you give it a cell, it gives you a polygon. You can do binning, where you have a bunch of points and it's going to do an aggregation, making these kind of visualizations for you. Yeah, there's a lot here. I haven't actually had the chance to play around with all of them, but it's super cool to basically see people build on top of something that I've been doing. Because essentially that's where I would like this to get, for it to become like an ecosystem that everyone can kind of get involved in and build on top of. And that's why I've chose to release it in this way. I've tried very hard to make like an engaging website, which has got like interesting visualizations of the internals, not just to understand the things better myself and to educate people, but also to make it easier for people to like collaborate and contribute, because I find this much easier to understand than like low-level maths code.
So where can, I mean, obviously, as we're talking and recording this now, I saw the same QGIS kind of implementation, I think yesterday, like you said.
Yeah.
And there's increasingly more ways for people to start to interact with that. Can you talk a little bit about where you see this going, and your next steps to take this? Because you've cleared all these big hurdles when it comes to a global gridding system, right? And we've covered all of those. What comes next? And then more importantly, how can people really start to kind of engage and start using this in their regular work?
So there's definitely kind of improvements that can be made to the core library. It doesn't have as fully featured an API as some of the competing ones. So I would like to work on that, but more than anything, I want to try and sort of promote this and get people to know that A5 is out there, and for them to start using it and giving feedback on it, essentially. So I think if there's data scientists out there, then I would just encourage them to take this, have a play with it. We have a Slack channel, we have GitHub repositories. If you want to report or contribute anything, then I'm be more than happy to discuss that. Likewise, if you're maybe like a data provider, then it's super useful if you could convert some of your data sets into A5, and then people can pick them up and use them directly in their analysis and play around with them. In terms of the visualization, then one announcement that I'm quite excited about is that in DeckGL, there is going to be a new layer dedicated to A5. So this is going to come in DeckGL version 9.2, which should be out in the next week or so. So this is going to make it very, very easy to visualize all this kind of data set, data with A5 in the browser and share them. And I would just like to see what people do with this, because my background, if I'm honest, is this kind of visualization, it's this mathsy side of things, but I can't do all of these things like myself. I'm not like an expert data scientist. People ask me like, what amazing problems could you solve with this? And I have like some idea, but I'm not doing this like every day. So I would love to see people try and like apply this to some of the challenges that they have at work and sort of see how it works for them. Because it's one thing talking about things in abstract, but it'd be very nice to get some kind of use cases, case studies of people using it out there. And also to back this up, I'm planning on writing an academic paper on this to kind of contribute in that way as well. This is not so much the world that I'm from, but I've had some really great conversations with other people working in this space. In particular, Jerome St. Louis, who's working on another project called DGGAL. He's been like a great person to nerd out over this about, and has really helped like achieve some of the things that A5 can do, in particular when it comes to the projection, and really getting this kind of true equal area. Then that was kind of like the last kind of like cherry on top to make it absolutely perfect. The system I had before that was good, much better than the kind of distribution of H3, but his kind of like the projection that has been used there really made a difference.
Yeah, I definitely recommend people start to check out what you already have, because you already have, these different tools you can start with right now in different languages, and you can effectively create that and then quickly visualize and do quite a bit already to start to add A5 into regular workflow. And I think particularly I want to hone in on like the two groups that you called out specifically, from the data scientists being able to quickly use, aggregate, analyze data. There is a certain value in being able to group and use that and do some different things from that perspective, and then also having the knowledge of the soundness of all the work that went into this, from the area to the sorting to all these different things. So that's one piece I think is going to be really important there. And then for data providers, again, to really kind of get people adopting and using, I think if you are creating data, being able to provide that and connect that into analysis immediately makes a lot of sense. So it makes that kind of a easier transition for people. Once I started seeing, various indices show up in provided data sets, it can allow you to jump steps forward, especially if you've already kind of adopted that as a base. And it's just another kind of important piece in language that can connect all that data in. So yeah, I'm excited to see where things are going to go, and hopefully just help people understand, what this is and where it fits in, and also all the important pieces that went into that, from making models and kind of just understanding all the dynamics, to now a fully implemented system that's ready to use. And once again, I think all the small choices that are important that can build up to something really impactful is kind of the way to think about it. And all those little pieces are important. And that's one thing I really wanted to call out here, is because while things on the surface might look similar, and they might look like they kind of have, some, overlaps and things like that, there's a lot of small, very important steps and choices. And I think, hopefully this helps explain all that, because that's what really impressed me, is going back all the way to, discovering the paper and building these things out, and then all the benefit you get from that downstream just as a user is really important. So, I mean, kudos to, first of all, thank you for putting all this together and building all the work that went into that, because I think these things are important, and I hope that these discussions help to kind of showcase that, all the work that went into that. And from here, where can people kind of stay engaged? Obviously, the A5Geo website, I'll include that in the link in the show notes. Where else can they kind of keep in touch and understand where things are going from here?
So the website is a great place to come and learn. If it's more like technical things, then I would point people towards the various GitHub repositories, or if they just want to like join and just chat, then we have a Slack channel. I think that's a great place to go. Just to pick up on, I think you made a very good point there. Like at a high level, then in some ways, this looks like very similar to existing systems. And that's kind of by design. I think this is something that's really cool about these grid systems is that you can reduce a lot of complicated math to basically, I have a cell and I have some value. So if you are used to doing some kind of workflow with something like H3, then it's going to be a very similar workflow. Maybe you can pretty much use the same code for A5 or any other grid system. And this is actually where I'd like to see this space go in the future, like whether or not A5 is part of it, that there are just like a larger choice of grid systems and people kind of understand when to pick and choose different ones depending on the problem that they're trying to solve, but not feeling like, oh my God, it's so sort of complex that I have to switch from one format to another. Like having higher level building blocks made on the top of like these like different low level kind of mathematical models.
Yeah, I totally agree, because when I think back to like my earliest days working my geography classes, one of the first things you're taught is to understand the trade-offs and choices between projections, right? There's different reasons you choose different projections in different areas, and you're making a trade-off between, are you sacrificing distance, or are you sacrificing, shape or area, all these different things that you're sacrificing. We haven't done that with grid systems, and I think that's going to be really important because it's becoming such an important part of not just the geospatial data lexicon, but like the data lexicon in terms of like the way people are talking about and connecting and using data. So I'm happy that we were able to kind of have this discussion. If make sure to check the links, and I'll include everything there so you can kind of follow along. But yeah, Felix, thank you again for all the hard and detailed work it takes to put something like this together. And for coming
really
on and talking a little bit about this.
Yeah, great. Thanks so much for having me on. It's been really good.
Yeah. All right. Well, we'll talk soon.
All right. See ya.